right? And you know, we're in chapter 7. We're talking about differential equations, and now with section 7.3, you learn how to solve separable differential equations. In section 7.4, we look at more types of differential equations that deal with exponential growth and decay. And those differential equations, it turns out, those will also be separable differential equations. Now I'll make a comment. You know, we're gonna move in at, like, when we're done with section 7.4, we're not going to cover the last two sections in chapter 7. Section 7.5 is logistic equation. Section 7.6 is predator-prey systems, and those deal with differential equations like logistic models, deals with like populations where you have carrying capacities, and then predator-prey models deal with where you have systems of differential equations with two like competing species or that sort of thing, or a prey and a predator. It's fascinating material. I wish we had time to cover it, but it will be covered in when you take differential equations, or if you take differential equations, Math 282. Ideally, it should be covered there. But for now, we're going to, you know, stick to 7.4. So, okay, let me give you a moment to copy this example down, and then we'll discuss it. Okay, so let's see what we have here in this problem. All right, so a common inhabitant of human intestines is the bacterium E. coli. Okay, how many of, so Escherichia coli, I hope I'm pronouncing that right. It's referred to E. coli. How many have heard of E. coli before? Okay, good. Javier's heard of it. Taj has heard of it, and you know, it says a cell of this bacterium in a let me see here, one moment. All right, a cell of this bacterium in a nutrient broth medium divides into two cells every 20 minutes. The initial population of a culture in this case is 60 cells. We want to find an expression for the number of cells after T hours, and then find the growth rate after T hours. Okay, so for this problem here, what do we need to do the problem? What is missing? What is missing from this problem that we need? In other words, if I say let YT be the population of E. coli after T hours. Okay, I mean that they want us to find an expression for that number of cells. So by population, I mean number of cells. What do we need to find this y of t? What do we need to, in order to get that solution, to get that formula that for the population of E. coli after T hours? What's our starting point? What's always our starting point in chapter 7? What do we need? Okay, good answer. We need dy dt. We need a differential equation. We need a differential equation. And it turns out in this problem, the rate of growth of the population of E. coli is proportional to the population of E. coli at time t. dy dt is equal to k times y. This differential equation is the differential equation that will model exponential growth or exponential decay. Exponential decay, for instance, would be if you had like a radioactive isotope that's decaying over time. How many remember exponential growth and decay from like pre-calculus or maybe another class? They've seen exponential growth, exponential decay. Okay, Tosh remembers that. Jan remembers that. Javier remembers that. Absolutely. And Ethan remembers that. And so, you know, in those problems, in those classes, you were given a formula, maybe for that you know, this formula is for exponential decay, but you never really maybe knew where it came from. So it comes from the differential equation. So whenever you have exponential growth or exponential decay, the differential equation that models that is dy dt equals k times y. If the rate of growth is proportional, okay, proportional to the population, okay, meaning if the population increases, the rate of growth really increases, right? That is the model for exponential decay. Now, what we need to do is we need to solve this differential equation, dy dt equals k times y. So what I'd like to do is I'd like to go to the whiteboard, and this is going to be part of your notes. I'm going to solve the differential equation, and you know, we're going to start the solution there, and then we'll continue here. So let me get the whiteboard up. Okay, and I will clear this here. Okay, so solution. And let me change the font here. About 3, okay. So we're given that dy dt equals k times y. And is this differential equation separable? I mean, we want to find the formula, you know, what's y of t equal to? Okay, so let me just so is this differential equation that models the bacteria growth, is it separable? Can we separate the variables? Absolutely. Absolutely we can. Anne's just right on that. So let's go ahead and separate the variables. So what I'll do is I'll multiply by a dt on the right and the left. So dy then would equal k times y dt. And then I'm going to multiply both sides by 1 over y. So separating the variables, I want to get the y variable terms on one side and the t variable terms on the other side. So this means then that 1 over y dy will equal, the y's cancel on the right side, that will equal k times dt. And now, of course, we're going to integrate both sides of the differential equation. Okay, so trying to solve for y of t. All right, so let me rewrite that equation. The integral of 1 over y dy equals, I can pull the k out, the integral of k times dt. K is a proportionality constant, right? We actually call k a relative growth rate. That's what k is called. So what's the antiderivative of 1 over y on the left side? Good, that's right, D'Angelo, the natural log of the absolute value of y. And the antiderivative of 1 is t. And then, we know that both sides give their own constants of integration. We can combine them, and we can, on the right side, just have a c1 there. Now, actually, here, the natural log of the absolute value of y could just be written as the log of y. We don't need to have the absolute values because y is positive, right? Y represents the population of E. coli. You can't have a negative population, so the y here is positive. All right, so here we are. Are there any questions so far up to here? Okay, well, so what do we do now? What do we do to solve for y? What do we do to both sides of the equation? How are we going to get the y? Okay, that's right, Tosh. We're going to exponentiate both sides. Sorry, let me turn this off. Hold on. I had to turn that off. Okay. So hold on. Let me put my cell phone on hold on. Let me put it on silent here. I never get calls during class time. Well, I do. I get house calls, but I don't get cell phone calls, right? So hold on. Let me just put this on silent there. Good. Okay, that'll take care of that. Let's continue. So, okay, we're exponentiating both sides of the equation. And e to the log of y becomes the log of y. And on the right-hand side, you have e to the kt times e to the c1 power. All right, and e to the c1 power you can write as c2. So now you have the log of, I'm sorry, I made an error here. Hold on. There's no log. try to erase it. Sometimes the mouse is better for erasing than the stylus. Okay, so y is equal to C2 times e to the kt power. Notice here, so you know, we have then that y of t is equal to C2 times e to the power kt. So we have a formula for the population, but it's like a family of formulas. We have a very specific E. coli strain here, so we need to figure out what these constants are, what C2 and C1 are, or C2 and K are. Well, remember initially at time 0, what's the population of E. coli? How many cells do we start with? That's right, Ange, 60. It's given in the problem. So that means then that 60, you know, here I'm using now the formula, 60 would equal C2 times e to the power of 0 times t. So 60 equals C2 times e to the 0th power, but e to the 0th power is just 1. And so 60 equals C2, and therefore now we have that y of t equals 60 times e to the kt power. So we were able to solve for one of the constants. What's left now is the constant k. Are there any questions so far? All right, well, so what piece of information, is there another piece of information that might help us here with K, finding K? What other, you know, we have to use all the information in the problem. Taj says, okay, well, it says in the problem that that a cell divides into 2 cells every 20 minutes. Every 20 minutes. So we're going to make use of that. What I want to do is go now. You know, I have the problem written out like on paper. So I want to go to the paper. But are there any questions before I go to the paper? We're gonna now, you know, here's like our, when we get to the paper, here's our starting point. Okay, then let me get back to the paper solution. Okay, so let's go to the solution. Okay, so this, I always have to change the font every time I go back in here. That's fine. So we're letting y be the population of E. coli after t hours. And this was the differential equation. dy dt equals k times y. That models exponential population growth. And the initial condition was y of 0 equals 60. So this part here, all of this part here, okay, we did this. This was did on the whiteboard. So you don't need to recopy that. And here's where we're starting. Y of t equals 60 times e to the ktth power. Now what we have to find is the relative growth rate, k. And after 20 minutes, okay, I'll zoom this up a little bit. Yeah, after 20 minutes, the population doubles. Okay, after 20 minutes, right, the population doubles. Well, how many cells did we start with? How many cells did we start with in the problem? 60. That's right, Ange. Well, double 60 is 120. So 120 would equal 60 times e to the power k times 1/3. Now I'm putting in 1/3 here. Why am I not putting in 20? I'm not putting in 20 minutes. I'm putting in 1/3. What's 1/3 come? Where's that come from? That's right. That's right, Tosh. 20 minutes is 1/3 of an hour. Remember how we defined the variable y. It's a population of E. coli after t hours. So 20 minutes means 1/3 hour. And so now I have an equation I can solve for k. I can solve for k. So we can divide both sides of this equation here by 60, and that'll give us 2 equals e to the power 1/3 k. We'll take the log of both sides, right? So if we take the log, the log of 2 would equal the log, natural log, because it's base e, the natural log of e to the 1/3 k power, and the log of e to the 1/3 k power is 1/3 times k. So we have then, all right, we have 1/3 k equals log of 2. K equals 3 times the log of 2. But we can write k a little bit nicer way. Now, WebAssign would accept the relative growth rate if you wrote it as 3 times the natural log of 2. But remember, from your pre-calculus days and your knowledge of logarithms, that a to the bth power, I'm sorry, the log, well, I mean the natural log of a to the bth power is b times the natural log of a, right? So we can write 3 times the log of 2 as the log of 2 to the 3rd power, and that gets us the log of 8, which we substitute in now for k in our y of t formula. Are there any questions? Any questions so far? Okay. Well, so okay, we have here we have an answer, but we can make the answer look a little bit nicer, right? I mean, what we have here, and maybe I'll circle this in green, is we have e to the power log of 8 times t. But I could rewrite that as e to the power log of 8 in parentheses times t. Okay, it's the same thing because you're multiplying the exponents. But e to the log of 8, this part here, e to the log of 8 is just 8. So we get 60 times 8 to the tth power. So you see, this is really a much nicer formula. Okay, when we say y of t is 60 times 8 to the tth power, it's just a nicer formula. It helps give you an idea of how fast this E. coli is, growing, right? 8 to the teeth power, you know, after every hour, you know, the population, well, grows according to that speed. So, you know, so it's just a little more intuitive. Let me see. D'Angelo says, "Why did it go to the power instead of being multiplied?" Hang on. Let me erase here. One moment here. Let's see. Can you show me, D'Angelo, where you're focused here? It's on the bottom there. Are you thinking about going from here to here? You're a little uncomfortable with that? Below that. Oh, here. Okay. All right. All right. I tell you what. Let me write over here. So y of t is 60 times e to the natural log of 8 raised to the teeth power. Try to make that a little nicer here. Okay, so what is e to the natural log of 8 equal to? If you take e and raise it to the natural log of 8, it equals 8. It equals 8. Equals 8. And so you get 60 times 8 to the teeth power, which I write then like this. But D'Angelo, does that help you feel more comfortable with that? Um, no, no. Well, T though, you see like the parentheses, and I know Mauro, you have a question. Just hold on a moment here. The e to the log 8 is in parentheses, so it's like in its own little world. I'm just simplifying e raised to the power natural log of 8, and I get 8. T is just sitting out there, and it's because, see, I can write e to the power of t times the log of 8 as e to the log 8 in parentheses times t, you know, because you're multiplying the exponents. It's the same. When you raise to a power, we're raising to the teeth power here. You just multiply the exponents, and then that would get you this result. So, Mauro, t times the natural log of 8 would, let's see. Yeah, I didn't think about that. Mario's saying that, hold that thought, hold that thought. Mario's saying this. Let me show you what Mario's saying here. Mario's saying that we could go from here and write this as 60 times e to the natural log of 8 to the teeth power. That's absolutely right, because t times the natural log of 8 is the log of 8 to the teeth power. Absolutely, that's true. And so there you get 60 times 8 to the teeth power. That's definitely another way to do it. Okay, good, Mario. Thank you. How many like Mario's way, like this way here, to get to the final, the nice answer? How many like that way? People are different, but you know, makes sense. Taj is liking it. D'Angelo's liking it. All right, great, great. Very intuitive. All right, Taj, very good, very good. So, okay, well, look, we have this formula. We have this formula, this y of t formula that tells you the population of E. coli or the number of cells of E. coli after T hours. Now we want to find the growth rate after T hours. Okay, that's the next part of the problem. Find the growth rate of the E. coli population after T hours, or after 10 hours. So if I'm going to find a rate, a growth rate, what do I need to work with for a rate, a growth rate? What does rate mean? What does rate mean in calculus? A rate is the same as a slope. That's right, D'Angelo. And a slope is the same as, that's right, Ditaj, a derivative. So a rate is a derivative, and a derivative is in turn a slope. So what I need to do is I need to find the derivative of this y of t. But I already have that. I have the differential equation. Okay, I have the differential equation, right? So let me just see here. So let's remember that dy dt was equal to k times y, and the k was the natural log of 8, and y is 60 times 8 to the teeth power. So this would give us 60 times the natural log of 8 times 8 to the teeth power. Let me just this here is k, and this here is y. So this is how I get then, this result here. And so after 10 hours, the growth rate is, okay, well, what's the growth rate? Well, what we have to do, right, is we have to put in t equals 10 in the derivative. We have to put in t equals 10. So I'm sure, I have it written down, but I'm just making it maybe a little more neat. Find dy dt when t equals 10. And so, okay, we substitute in the 10 here. And wow, we end up getting, what notation is this? 1.3397 times 10 to the 11th power. What notation is that? Do you remember? I'm sure you've had chemistry. Well, you've seen this in math too. What kind of notation is that? That's right, Javier. Very good. Very good, Jan. Very good, Ange. Scientific notation. Okay, so now let me see here. I'm now the units, of course, the units, it's important. The units are cells per hour. Cells per hour. It's a rate. I'd like to go into Desmos and type in this 60 times the natural log of 8 times 8 to the 10th. Okay, I'm going to go in Desmos here, and I'll probably make that part of the recording too. Let me just bring up Desmos. So I'll come back to this. Are there any questions up to here? Okay. Okay, what I'm going to do, I'm going to go in Desmos, and I'm going to type in 60 times the natural log of 8 times 8 to the 10th power, and see if it gives me this scientific notation. Like the TI calculators, for instance, will use an E, a capital E, for scientific notation. But let's see what we can get here in Desmos. All right. So hold on here. Let me and then we'll come back. Here's Desmos. Okay. So let's see. 60 times the natural log of 8 times 8 to the 10th power. Wow, look, there it does it. See that? Look at that. It gives us 1. If we round, 1.3397 times 10 to the 11th power. So that's actually nicer than what the TI calculator does, because the TI calculator will have like an E instead of the times, but they mean times. But how many have seen scientific notation in like the graphing calculators, or even just a basic calculator? They have like usually an E comes up. How many maybe have noticed that? Okay, Mario and Anch have, and it's fine, you know, perfectly fine. But Desmos does it nice here, so I kind of like that. I like that. Okay, well, on that note, then let me get back. Let me get the you know, our example back here. This is all in the recording. So okay, here we are. Now, what happens is the like WebAssign for your section 7.4 assignment. Okay, that's going to be due on Sunday. That like they might say, well, give the answer in terms of billions of cells per hour. Okay, so what we can do is, you know, how can we get billions of cells per hour? How can we get it to look like that? Well, what we can do is we can take the 1.3397, leave it there, and then the 10 to the 11th power, I can write as 10 squared times, let me just hold on here. Let me clear this. I want to write it a little more nicely. Okay, I can write this here as 1.3397 times 10 squared times 10 to the 9th. So I'm choosing to take 10 to the 11th power and write it as 10 squared times 10 to the 9th. Now, why would I want to do that? Well, I'll show you. So 10 squared is 100, and 100 times 1.3397 is 133.97. So you get 133.97 times 10 to the 9th. That's what I have written here. And 10 to the 9th is what? 10 to the 9th equals, does 10 to the 9th equal a million or a billion? A billion, right. 10 to the 6th is a 10 to the 6th power is a million. But if you have 10 to the 9th power, that's a billion. That's a billion. Okay, billionaires have a lot of money. Okay, so you get 133.97 billion cells per hour. And this might be how WebAssign wants you to write the answer. But if you write it all out with the zeros, this is how many cells per hour. This is the rate. 130, let me see, that's 100. Wow, that's 133 trillion, 970 billion cells per hour. That's the rate of growth after 10 hours. The rate of the rate at which E. coli is growing. per hour. Yeah, Mario, that's right. And that's why, we have to be very careful on bacteria growth. That's right, Mario. It's really quite amazing. How many notice like in, well, we have like restaurants have, there are health codes, right? How many have seen like you go to the bathroom and there'll be a sign that says employees wash your hands. How many have seen that? And really everybody should wash their hands, right? Um, uh, but how many have noticed that? Maybe some places. Sure, Jan and Ange and Ethan, and it's because they don't want the employees, if they go to the bathroom and, they don't want to risk the employees, maybe their hands aren't clean and then they handle food and then bacteria gets in the food and it grows and you're going to have a big problem. You see, so it's a very serious matter. The like exponential growth. And that's why we have a health departments, uh, to make sure restaurants are following the rules and people don't get sick, right? And so I actually heard, I don't know if this is true. I keep hearing that like only 1 in 4 people wash their hands after using the bathroom. I can't believe that. And do you think that's actually true? That only 1 in 4 people wash their hands after using the bathroom? I don't know. Um, I think it's more than that personally, but I don't know. You know. But at any rate, uh, yeah, I think Javier agrees with me there. So, but one very nice thing about this problem uh, that you saw too is that we started out with a differential equation here with an initial condition, and eventually we got we got an expression for. Hold on, where's my stylus? Hold on, where did I put it? Oh, here it is. We got, when we were done, an expression for population growth. How many, well, we have a formula. How many recall seeing formulas like this in pre-calculus when you covered exponential growth? Formulas exactly like this. Sure, Mario remembers that, and D'Angelo remembers that, and Jan remembers that. But now that you're in calculus 2, you know where that comes from. You know that that formula just didn't come out of thin air. It came from a differential equation that is used to model exponential growth. If you have an exponential growth, that means the rate of growth of the population is proportional to the size of the population at time t, and that then generates that formula that you saw. So you have a more in-depth understanding of the exponential growth. And another thing too, I'll mention in section 7.4, we now have all the problems deal with either exponential growth or exponential decay, and so all the problems can be formulated in terms of this differential equation. And being we solved the differential equation, we solved it once already. Could we sort of put just kind of a general formula that that we could just utilize in 7.4? And the answer is yes. So let me bring that formula up here. I'm bringing up 7.4 on the ebook. Okay, so let me see here. Let me go to the ebook. Okay, so if we have an initial value problem, and this is in section 7.4, okay, if we have initial value problem where dy dt equals k times y, and at time 0, the initial population or amount, it could be amount of radioactive material, right? The initial amount is equal to y sub 0. Then in general, the solution to the differential equation is y of t equals y sub 0 times e to the kth power. Okay, and that's the kind of formula that, again, you saw when you took pre-calculus, but now you know where it comes from. And they solve the differential equation. They solve it just like we solved it for our example. They solve it below, and when they solve it below, they get to the result. So you can utilize this formula in section 7.4. I mean, I would be, of course, very happy to see you in 7.4. You start with the differential equation, separate the variables, and solve. But the thing is, it would be a little repetitive because it's the same, basically the same differential equation for every problem. Now, sometimes you have to, like for instance, if you have like Newton's law of cooling, that's example 4 in section 7.4. You can adapt that formula so that it works with this, so that differential equation is like the differential equation you see here. And they show you how to do that in example 4. And in your homework for section 7.4, I believe most all the problems have like a watch it video or a help aid. So I think you're going to be fine. I want to get to our break here because we need to talk about section 8.1. But I want to give you a little time to work on classwork too. So are there any questions before I stop the recording? Who's feeling good? Who's feeling good so far with section 7.4? Okay, good, excellent. Taj, Javier, Ethan, Jan, wonderful. Well, good, because it's a very important section as well. All right, I will stop the recording. Okay.